Okay, cool. Let's come back. Okay. Let's start talking about one more sorting algorithm. Okay. Very interesting discussion going on. Let's continue that. Now, the next sorting algorithm that we are going to take a look at is also one of the very famous sorting algorithms, bubble sort. Now, the bubble sort is one of the most simplest sorting algorithms. To understand bubble sort, you have to understand how exactly bubbles work in a tank. Let's say if you have a tank of water, right? And let's say there is a opening from which a lot of bubbles are being created, right? A lot of bubbles are being created. Now, if you know simple physics, but even if you don't know simple physics and you know simple observation, then the biggest bubble comes to the top of the surface first, right? The biggest bubble comes to the top of the surface first. And this is the basis of the bubble sorting algorithm. Okay. Whatever is the biggest bubble, that will travel the fastest and move to the top first. The smallest bubble will come to the top later. On this scenario only, bubble sort is prepared, right? So let's try to understand bubble sort. Let's take an example like this. Okay. Consider every element of your collection. Consider every element of your collection as a bubble. Consider every element of your collection as a bubble. What you have to do is, in every iteration, you have to push the biggest bubble on the top. Okay. In every iteration, push the biggest bubble on the top. And when I say biggest bubble, I'm referring to the biggest element. This should be your sole agenda, right? This should be your sole agenda, that you push the biggest bubble to the top, right? Or you can say you push the biggest element to the top. Okay, cool. Now, how do you do that? We start with the first element. We do not know whether it is the biggest element or not. So what we will do is, because just think about it. If let's say there are different bubbles in the race, you will compare this bubble with the next bubble. And if it is a bigger one, you will move it ahead. Same thing here. You're going to compare 5 with the next adjacent element. Is 5 bigger than 4? Yes, it is. So what you're going to do is, you're going to swap 4 and 5. Then you compare 5 with the next element, because you're pushing it up. You're pushing it up, so you're constantly comparing it. Is 5 greater than 3? Yes. You swap 5 and 3 again. Then you compare 5 and 2. You swap 5 and 2. Then you swap 5 and 1. You swap 5 and 1. And can I say, when one iteration lasts or ends, when one iteration ends, your biggest element is at the last. And this becomes the sorted region. This is the unsorted region, right? This becomes the unsorted region, right? So every time what you do is, from the unsorted region, you take the first element and you try to push it to the last. Let's try it again. Is 4 greater than 3? Yes. You swap it. Is 4 greater than 2? Yes. You swap it. Is 4 greater than 1? Yes. You swap it. And that's it. You are now at the end of the unsorted region. And after this iteration, can you see? This is the unsorted region. This is the sorted region, right? And so on. So that's the basis of bubble sort. Okay. So let's say you have something like 4, 3, 2, 1. In bubble sort, what you do is, in every iteration, you try to push the biggest element to the top. And you try to check from the first element only. Now, for example, let's do something like this. Let's say we have something like, let's say this is the array. Okay. Let's start putting bubble sort here. Is 3 greater than 4? No. Is 4 greater than 2? Yes. You swap. Is 4 greater than 1? Yes. You swap. Then you repeat again. Is 3 greater than 2? Yes. Is 3 greater than 1? Yes. Now again, is 2 greater than 1? Yes. And can you see at the last you have the sorted region? Everything is sorted. So what you do is, in bubble sort, you do pairwise comparison. We do pairwise comparison, right? Whoever is bigger is shifted to the right. Whoever is bigger is shifted to the right. And that's it. Now, let's try to code this algorithm. And once we have coded this algorithm, because you can see we are doing very simple thing here, we'll try to analyze a few things, okay? So first thing first, what I'm going to do is I'm going to write a simple pseudocode for you, okay? Like on the pen and paper, how it should look like. I'll say for I equals to 0, I less than n, I plus plus. We'll go to, we'll try to do n iterations, okay? For every iteration, we'll say for j equals to 0, j less than n minus I minus 1, j plus plus. Now this is interesting. Guys. What is n minus I minus 1? And you can say j less than equals to, or in fact, you can do j less than n minus I, okay? What is going on with j n minus I? Let's try to figure it out. Let's say you have an array like this, 4, 3, 2, 1, okay? Currently, I is equals to 0. That means you are in the 0th iteration. In the 0th iteration, what do? You put j here. And what do? You compare j with j plus 1. Is element at j greater than j plus 1? Yes. So you swap the elements and move j ahead. Is the element at j greater than j plus 1? Yes. You swap the elements and you move ahead. Is the element at j greater than j plus 1? Yes. You move ahead. Can I say that's it? You do not need to do anything else. So the moment j reaches the second last element, you can stop there, because the moment j moves ahead, there is no j plus 1, right? So technically j should end here. And this is the 0th iteration. So j is ending at n minus 2. And we can write n minus 2 as what? J less than n minus 0 minus 1. That's why I wrote n minus I minus 1. You can see when I is 0, this is n minus 0 minus 1. J less than n minus 0 minus 1. That is j less than n minus 1. That means n minus 2. Let's try it again. Let's try it again. When I is equals to 1, you are at the first iteration. You start with j equals to 0 again. Is j greater than j plus 1? Yes, you swap. Again, is j greater than j plus 1? Yes, you swap. And that's it. We should stop here because the remaining part is now sorted. So what is this index? N minus I minus 1, that is n minus 1 minus 1, that is n minus 2. So you do j less than n minus 2. What is j less than n minus 2? N minus 3. Can I say this is n minus 3? For example, n is equals to 4. 4 minus 3 is 1. Can I say the last index of j is what? 1? Right? So that's why I wrote it like this. And here, what do? We compare. If a of j greater than a of j plus 1, you swap a of j and a of j plus 1. That's it. That's it. That's how you write bubble sort. But we can do small optimization. Let's think about it like this. Let's say if you have a completely sorted array. I is equals to 0 means you are at the 0th iteration. You start with j here. Okay? You start with j here. Is j greater than j plus 1? No. No swapping. You just move j ahead. Is j greater than j plus 1? No. Then no swapping. You move ahead. Is j greater than j plus 1? No. No swapping. Is j greater than j plus 1? No. No swapping. Can I say in any loop of j, the moment we realize that no swapping occurred, we can say the array is now sorted. The moment we realize that no swapping actually occurred, the array is already sorted. Can I say that, guys? Yes or no in the chat? If at any point of time, if in the loop of j, no swapping occurred, then array is sorted. So how can I do that? We can take a Boolean variable is sorted as false. And if any swapping occurred, if you land up in this if check, then swapping occurred, you can say, and we should not say is sorted, we should say is swapped. We can say is swapped as true. We can do is swapped as true. And at last, you can check. At last, you can check that if is swapped is equals to false, that means the array is already sorted. You can return. That's it. That's it. Can I say that, guys? After the loop of j, I will check that whether in the loop of j, any swapping occurred or not. If no swapping occurred, then I will return from the function. Right? So just think about it. If the array is already sorted, when you're at I equals to 0, you go here, you go here, you go here, you go here, you go here. You did n operations for comparison. Can I say that? You go till n minus 2. So approximately n minus 2 is n only. You did n comparisons, no swapping occurred, and you exited. So can I say for bubble sort, the best case scenario becomes omega of n? Because you can see here, I am not separately checking. The best part is I am not separately checking that whether the array is sorted or not. In the algorithm only, we found a way that, oh, if this thing worked, then the array is already sorted. There is no provision of anything like that in selection sort or any other sorting. That makes bubble sorting special. That the best case of bubble sort becomes omega of n. That in case your array is sorted, you do not need to do extra effort. Bubble sort automatically detects that. Otherwise, if the array is not sorted, what can be the worst case? Think about it. 5, 4, 3, 2, 1. For pushing 5 at the last, how many swaps? 1 swap, 2 swaps, 3 swaps, 4 swaps. Can I say we did n minus 1 swaps? Then pushing 4 at the last, 1 swap, 2 swap, 3 swap. That means n minus 2 swaps. Can I say that? Then for pushing 3, you have n minus 3 swaps. Then for pushing 2, you have n minus 4 swaps, and so on. So this is what? N minus 1 plus n minus 2 plus n minus 3, so on and so forth, up till 1, where you will realize. Here you can see for the second last element, you just need 1 swap. You just need 1 swap. Right? You just need 1 swap. So how many swaps occurred? Can I say this is the sum of the first n minus 1 natural numbers? What is the sum of n minus 1 natural numbers? N into n minus 1 by 2. N into n minus 1 by 2 can be written as n into n minus 1 because 1 by 2 is what? A constant multiplicative factor. Then this can be simplified as n square minus 1 n. If n is 10 raised per 5, 10 raised per 10 minus 10 raised per 5 is what? 10 raised per 10 only. So can I say this is approximately equal to order of n square? So in the worst case, the bubble sort will go as bad as selection sort. But in the best case, bubble sort is better than selection sort. That is the beauty of bubble sort. Now let's try to code it, guys. Let's try to code it and see how it can actually work for us. So I'll create a new file, bubblesort.java. Okay. Now let's write a function, public static void bubble sort. We'll give it an array. For int I equals to 0, I less than n, I plus plus. For int j equals to 0, j less than n minus I minus 1, j plus plus. And what is n? N is length of the array. Okay, n is length of the array. Why j less than n minus I minus 1? Why j less than n minus I minus 1? Because in every iteration, we push the biggest element at last. Biggest element at last. So no need to compare that. And then we check if ARR at j is greater than ARR at j plus 1, right? We do int temp is equals to ARR at j. ARR at j is equals to ARR at j plus 1. ARR at j plus 1 is equals to temp. And that's it. And that is it. So let's say we take an array. We do bubble sort. And we print the whole array. If we try to run this code, can you see we are getting all the elements sorted. Now let's add the optimization. We can say bool is swapped is equals to false. And at any point of time, if any swapping occurred, this is boolean. If any swapping occurred, we can say is a swap to true. And at the end of the loop, we check if no swapping occurred. If no swapping occurred, then array is sorted. We can say if is swapped is still equals to false, we can return from function as array is sorted. That's it. If you run the code again, let's say for 1, 2, 3, 4, 5, you can see we still have the sorted array, and this time this will make the case as big omega of n. How cool is that? Right. So this is a very simple implementation of bubble sort. All you do is just adjacent element swapping. See, this is the point where you are doing adjacent element swapping, right? Now you might be thinking, what would be the average case of bubble sort? Average case of bubble sort can be, let's say, instead of n square iteration, you take something less than n square, right? How less than n square? Some part will be randomly, let's say, sorted. Some part will be, let's say, unsorted. In overall, you do not go n, right? You only go omega of n when the whole array is sorted. Otherwise, you go something greater than n and something less than n square. So what we can say is that the average case is also n square only, right? On an average, it will be n square only. Why? Because the moment you do not simplify your whole array in one single shot, or you can say the moment you don't have a sorted array already, you have some randomly shuffled array. In randomly shuffled array, you will be having, let's say, some iteration less than n square, but definitely greater than n. So what is a good assumption to go for? If there is something definitely greater than n and less than equal to n square, can I say this will be overall n square only? Maybe you have something like n square minus n. N square minus n is also n square. N square minus 5n. This is also n square. Something less than n square, but not too much, right? So that's why we consider the average case of bubble sort also as theta of n square. So this is a very interesting website called as Big O Cheat Sheet, which talks about a lot of Big O Cheat Sheet, which talks about complexity of a lot of sorting algorithms and some famous algorithms. You can see the graphs of the overall structures. And if you carefully see, bubble sort has best case as omega of n, but the average and worst case are still n square. And you can see the comparison with some other sorting algorithms as well. Make sense, everyone? Yeah, sure. Let me share the link. I'll put the link in the GitHub repo only.